Hello and welcome to Hardware to Save a Planet. I wanted today to do a little look back at 2025 as we reach the end of the year. It seems like everything these days is about AI, and even though we don't hit that topic directly much on this show, it turns out a lot of our guests are developing solutions that are particularly relevant in the context of AI growth. Whether we're in a bubble or not, there's an insane amount of data center build-out planned to support AI in the coming years. With that comes both new energy demands and new demands for the raw materials like steel and cement to build out all the infrastructure. To do this sustainably and to ensure reliable performance, we'll need new sources of renewable energy, energy storage, and construction materials. I'm optimistic that these demands will actually add fuel to the fire of innovating and scaling new technologies to fight climate change. So we've collected a handful of clips from episodes this year to show some technology innovations relevant to the AI boom. Let's get started. First up, we have Arch Rao from Span. He talked about the challenges of our aging analog electric grid. Utilities build for a theoretical maximum peak load, leading to a hugely expensive and slow infrastructure upgrade process. Arch challenges that assumption by revealing that most buildings already have significant unused power capacity. He explains how Span's technology digitally manages loads real time, proving we can get a lot more usable capacity from our existing grid if we're smart about the loads. If I understand right, by being smart about when we apply these loads and making sure we stay under whatever the capacity of the existing grid is, by controlling what's happening behind the meter at the edge, at each home, we can avoid all this expensive infrastructure upgrade because we don't need all of these appliances to be on at the same time.
And in a way that doesn't actually impact your practical convenience, right? Because I'll give you a couple of numbers that I've shared in the past to sort of illustrate that, right? The average distribution grid in the US operates at about 42% utilization rate, right? In that you've already today upsized our distribution system based on a projected theoretical load that is far in excess of what our actual consumption is on a normal day, on a given day, right? That problem gets a bit more acute when you think about reverse power flow coming from solar export, et cetera. But regardless, the average utilization is about 42%, right? Layer on top of that, homes that we are in today, tens of thousands of homes across the US in all 50 states, and we've looked at this data empirically. An average, if you look across all 200 amp homes that are fully electric, 98% of those homes have 80 amps of unused capacity 100% of the time. Let me say that again, right? 98% of 200 amp homes have 80 amps of unused capacity 100% of the time. That means services are oversized because they're based on an analog math that we're doing. But if you look at it through the lens of the physics, it does make sense because you can't undersize an analog system, because what if I do draw 200 amps or worse yet, 225 amps or 250 amps at some point in time? I need to be... That's right. And same goes for 100 amp homes, 40 amps of unused capacity in 86% of the homes, 100% of the time, right? So the opportunity is there. And what we've done is really parse through the data to see what frequency and duration of load management do we have to do in order to avoid a service upgrade. And it ends up being 1% of the time, right? Less than 10 hours an entire year. 8,760 hours in a year, do I have to do the controls? And the average duration of a control event is about 6 minutes, right? So when your EV is on at the same time, your water heater is on at the same time, your electric dryer comes on, I'm going to derate your EV charger by 30% for 15 minutes or 6 minutes in a way that you didn't even perceive the impact of. And we're fully electrified. And that's the meat of what we've solved.
Next, we have a clip discussing the challenge of manufacturing and deployment, which needs to ramp up quickly to keep pace with projected growth. Anders Korsgaard of Blue World Technologies explains why developing hardware for the energy sector is fundamentally more complex than building software, illustrating the unique hurdles in bringing his innovative fuel cell technology to market. It feels to me like fuel cells, electrolyzers, like you said, batteries are very similar. Like this kind of realm of hardware is very common in a lot of these different solutions that are kind of about new materials production or energy storage or energy generation. And yet it feels like a lot of work goes into the kind of R&D and problem solving and early engineering in all of these solutions. Is this not something that we've kind of that is, the sort of fuel cell design is very mature and solved, and the challenges are less about the sort of engineering itself?
I think it depends on what industry you're in. So on the low temperature PEM and the pure hydrogen fuel cell modules and stacks and systems for trucks and cars and so forth, there's been invested billions of US dollar into that. That's really mature. That's really mature. Everything from the Toyotas and the Daimlers and those guys in this world, they invested so much cash into this. So that is really well developed. When you come into what is their problem is mainly on the getting hydrogen at the right cost. The promise of getting hydrogen for $5 per kilo has been there for as long as I've been in the industry, and they're still struggling to get below 15 or 20, right? So that would be a really sharp price today. And then in addition to that, you have all the tanks and infrastructure that's sort of, causing even for the big guys a lot of trouble to get that sustainable from a commercial perspective. So that's their challenge. Our challenge is basically also so there are definitely, we are less mature on system level, doing all the reforming, all the different system integration. That also takes some hours, so to speak, and it's more the sheer quantity of. It's not that everything is sort of reinventing the wheel. A lot of it has been done before, but you still need to adapt it to the specific application. So that is the challenge, I would say, of in particular the power to X or the fuel cell industry, is that the problems are so multifaceted as compared to maybe a battery, where once you have a battery cell and you have a BMS, then you fit in, I have a lithium battery with a BMS on my sailing boat, right? So it's super simple. I can just buy this box and put it in and replace a lead acid battery. And it's, if it fits in, there's nothing more to it. When you have a fuel cell, there's all sorts of other, systems, and complexity is higher compared to...
like the inputs and outputs are more complicated.
Exactly. So that's making this industry more challenging than a better.
To meet energy demands of AI compute, I imagine we'll see new sources of renewables scale. I spoke with Ina Braverman from Eco Wave Power about harvesting ocean wave energy. She shared that wave power alone could provide up to 66% of US energy needs. I know that some data center build-out is planned to be in or close to oceans, so it seems like there could be a good reason to look at ocean waves to solve part of the energy challenge. What's your vision for the future of Eco Wave Power? What do you hope to accomplish?
So I definitely hope to see as many projects being implemented as fast as possible. As the entrepreneur behind the company, like I hear many times, from external sources, from other people, that like, wow, Eco Wave Power is moving forward so fast. Like nobody's actually putting real conditions, installations. Like we have one running in Israel, we have now one in LA, we have projects coming in Taiwan, in India, and in Portugal, and everything is supposed to happen in the next 1 year to 1.5 years. Like that's a lot of project. It seems very fast. But to me, as a very passionate and I would say a little hyperactive entrepreneur, I would like to see it happen even faster, because there is a big potential. There are a lot of these breakwaters. They are not used for anything, again, other than breaking the power of the waves. Like, why not utilize all of them to produce power, clean electricity, and create clean jobs, which is something that the United States needs. Like all the recent studies are showing that jobs in the United States are not growing fast enough, and that we need to create more workplaces. like what will create more workplaces than an energy potential that can provide, according to the Energy Information Administration, 66% of the United States energy needs. So like everything like makes sense. The AI industry is growing. For United States to maintain its leadership in artificial intelligence, according to President Trump, the United States has to double the amount of energy it produces. So 66% potential energy from the waves, like I would give it much more attention and make sure that it happens much, much faster. And I really hope that that's the next phase, because I think that the more energy is needed to achieve technological progress, the more kind of sure that the government and the president and other states and countries in the world will open their eyes to new sources.
Next is Ted McElveen of Vern, which is tackling the critical role of backup power. He explicitly details why the current reliance on dirty diesel generators is a major challenge for the grid, and explains how hydrogen can transform these on-site generators into vital, clean grid support assets.
What about from a climate impact standpoint? You know, you said they're not running all the time, which is a good thing. Does that mean, like, how does that translate into sort of emissions, and how big of a challenge or how big of an impact to climate change replacing those with hydrogen would be?
Yeah, so I mean, when you do run it, it is incredibly dirty in terms of CO2, but also particulate matter, NOx, SOx, so all the smog causing and local air quality issues. So these backup power generators are actually not allowed to run that often. They're not allowed to run more than, well, it depends on the specific region, but more than 50 hours in most regions. And so you can actually turn on all these backup power generators in when it's installed as a backup generator. Why is that a problem? Well, I think the thing that everybody's talking about today is the data center power demand growth. And just a couple more numbers here. There's about a median forecast or central forecast in terms of how much new data center demand growth there's going to be is about 50 gigawatts in the next 5 years by 2030. So again, 50 gigawatts, that's about equivalent to the current power demand of the state of California. So we're about to add about another state of California's worth of power demand in terms of data center growth, load growth, which is really kind of a shocking number. But what people don't talk about is that each of those gigawatts of new data center has a gigawatt of backup power generation. Another diesel generators that are being installed on site at those data centers. So again, back to the question of why does this matter, and what can Vern do about this? All this data center load growth ends ending up being a very big challenge for the grid to handle. And it's really kind of unfortunate, the fact that they have these diesel generators that are on site, but that can't be turned on. You would like to be able to turn on those diesel generators or turn on some sort of generator to help support the grid if there's a big shortage of electricity on the grid, but they can't because they're so dirty. So with hydrogen, if you didn't have diesel generators, but instead you had a hydrogen generator there on site, you'd be able to turn them on if the grid needed extra power, extra support. We'd be able to turn those on and really support the grid and do so cleanly. So there's while currently those generators aren't run that often, and for good reason, because there's so much pollution, you actually could run these on-site power generators with hydrogen more frequently. And this isn't, it's not a small kind of corner case. We're talking about, like the size of power of the state of California just for the data center application alone. And then there's other diesel generators I should mention that do run, close to 24/7. And that's at remote applications. So things like currently drilling for oil and gas, those diesel generators, they use diesel generators because they're in remote locations. You can think of, the big oil fields, and they're running very major, big diesel generators, close to 24/7 for the drilling operations. Now, hopefully we do less oil and gas drilling in the future. We're still doing a lot of it now, but some of that might transition over to geothermal drilling or transition over to drilling for geologic hydrogen. So there's a lot of these remote power applications that do use diesel in a more continuous manner.
Solving the intermittency problem is key to achieving low-cost 24/7 clean power that can be intermittency from renewables like solar and wind, but also the intermittent demand for energy that data centers are expected to generate. Nihali Jain of Antora Energy shares her company's unique approach to energy storage, detailing how their thermal batteries can charge up to 10 times faster than they discharge. This capability is essential for data centers to smooth out the peaks and valleys of both supply and demand to operate as clean and efficiently as possible. You could blow air through your carbon blocks or something like that to transfer the heat out, but you're doing it with radiation. Is that what you mean? Yeah. Which I guess must translate to like the form factor of your batteries. You want to have all the surface area of the carbon blocks exposed when you open your door, right? To get as much radiation as possible.
Not really. That's a great question, though. That was my question as well when I was thinking about it. You don't need all of the carbon blocks to be exposed. You just need the right amount to be exposed, and you can optimize that. So we've optimized the system based on what is the power that the customer really needs, or how much power do we want one module to be outputting. And the rest of it just stays in. So really, it's a mathematical function where you want to optimize for how many hours of storage, how much output power do you need, all of that, and essentially with how much charging do you want to be at, how fast do you want to be charging your system. So these are sort of the parameters to think about. And for us, we've been able to optimize the amount of storage. We've also been able to optimize how fast we want to charge and discharge our systems. And right now, for the first product, we can charge 3 times as fast as discharging it, which means if you look at, if you want to be supplying 24/7 heat or power, to be able to supply it for 24 hours, we only need to charge for 8 hours. And all of this also it is not as if you're charging and then discharging. This keeps on happening simultaneously. And that really allows us to grab the lowest cost 8 hours of electricity. We've also done 6:1 charge to discharge ratios, and I think we can go up to 10:1. But again, it depends on which customer application we're trying to service and what makes most sense in that geography.
The next clip shows another take on energy storage from Curtis Van Wallachem of Hydrostore. He talks about the utility of long-duration storage. He explains that their advanced compressed air energy storage system provides essential grid stability services that current battery technology cannot. This will be crucial for serving the needs of data centers with intermittent supply.
I'm kind of curious about like the unit economics and like the round trip efficiency and what do they call it? Levelized cost of energy storage. How does this compare? You mentioned earlier how much cheaper it is to add additional kind of duration relative to batteries. Where does this sit sort of economically with other storage options?
So we compare mostly with pumped hydro and lithium ion because they're the most common solutions out there.
Mm-hmm.
At 8 hours, we have about a 25% lower LCOS than lithium ion.
Okay.
And about 15 to 20% lower than pumped hydro. Once you move to like 16 hours, we're about 50% lower than lithium ion. And again, about 25% lower than pumped hydro. For us, relative to pumped hydro, it's our ability to go where they can't go more so than our cost advantage. But with lithium, it really is a lower cost because we have a much longer life. Now, batteries are more efficient. We're about 65%. They're about 85%. They can be built faster. We take about 3 to 4 years to construct. They can go anywhere. We can only go to a third to half of landmass. And they can be built at any size. We have a minimum size. So there's still a lot of reasons why batteries are going to have a big run. But where we compete, where you do need 8 to 20 hours of storage, you need 500 megawatts, and you're planned far enough in advance that you can have a 4-year construction, we do offer a better, drives more local labor, lower cost, longer life, and we bring synchronous inertia because we use synchronous motors and generators. So we provide a lot of grid reliability services that batteries just are not very well placed to provide as well.
Okay, can you explain that? What do you mean by synchronous motors and generators?
So the grid requires inertia at all times, and inverter-based technologies, solar and batteries predominantly, can't provide that. You need spinning mass. So it's historically been provided by coal, gas, hydro, and nuclear assets. But as more and more wind, solar, and batteries are coming on, they quite often don't have enough inertia. There's some talk of batteries doing synthetic inertia, but it really doesn't, it's not the same thing, and it impacts the battery's ability to do other things. So in some places like Australia, if you want to build a new solar farm, you have to bring in a synchronous condenser, which is just a spinning hunk of mass. It doesn't provide any energy. It's just providing inertia. Yeah. Our motors and generators provide that in plenty. So we give that as a service for free, just like a gas plant would give it for free today on the grid. So in markets that are heavy renewables, this is becoming something that they desperately need and are willing to pay for.
I know that some of the biggest companies driving data center construction have a goal to do so with limited greenhouse gas emissions, but the cost of green materials is going to limit their adoption. Sandeep Nijawan from Electra explains how their process produces pure iron for low-carbon steel making at cost parity. You mentioned cost. As I understand it, you're selling you're selling iron, like 99% pure iron to steel makers, or to Nucor as your example. Why are they choosing to buy your iron over other iron?
Yeah, I mean, look, at the end of the day, we have to supply this iron that is not only have lower emission profile, which is good for the environment, but do it in a way that is cost effective. So it has to be comparable to the way incumbent iron and steel can be made. So what we've shown is that our process has inherent advantages in economics that allow us to get to parity or near parity with how iron is being made today. And big part of those are economics levers that we are turning. What are those? One is about 40% of the cost of iron making today, you are feeding those high grades of ores that I mentioned. Okay. Now we are taking grades of ores that nobody is able to use. So that's 40%, which is an operating cost. We move that as a lever. Okay, great. The second largest operating cost in making iron is your cost of energy. Today we use coal. What comes closest to displacing coal is renewable as a resource. And there we don't seek a base load power. So we can work with utilities that when there is excess power, we can take that in. But if there is high demand for power on the grid, we can, in order of minutes, turn down the consumption of how much power we are consuming. So we become in a way grid balancing resource. So by providing that value to the system, as a result, we get the cheapest energy resource that then lowers our cost and economics to make essentially iron. And then we make not only, unlike other forms of iron, we make pure metal, whereas other forms of iron still have impurities in it, which need to be taken, processed downstream. So we only feed forward now pure metallic iron. So as a result, the industry and the customer actually gives us a price premium for giving a value to them and hence reducing their cost. So this is commonly done in steel industry. If you have clean, let's say recycled steel, you get paid more. Simple concept. The same thing if I don't bring impurity to you and you pay me more is the idea. So we get higher price. So you can start saying that we are controlling our inputs from a cost perspective, and then we are able to get higher premium on the output. And as well as what we're also doing is we are offsetting our cost for making iron by extracting what's in the impurities and feeding that as co-products as well. So we're looking for other value revenue streams as well to offset the cost of making iron, which is really what the world needs today. So that sort of provides a very good economic value proposition, and provides a pathway for making the entire value chain being more sustainable. Everybody from, an ore company that is sitting on that asset that is highly underutilized to a steel maker that is looking for something that is green and cost effective. Everybody wins along the way in the value chain. So that's a big aspect of it. The other is that as the world is transitioning from blast furnaces to electric arc furnaces, because that's only two ways to make iron. Either you can go with the blast furnaces or you go with electric furnace out. As the transition is happening, there is a shortage of iron units effectively that can be put into electric arc furnaces. So this industry is today, and the transition in the next 10 years is highly supply side constraint, where that with this transition, there's an opportunity to supply iron. Actually, iron doesn't matter what color it is. It's green, blue, whatever it is. And the industry will take it because just there is shortage of iron units to help with this transition, which is great news for somebody like us. You have the demand. So we are seeing that also on our end where we have announced MOUs and offtake with commercial and processing structures with many of our partners already. And we're seeing that on the demand side as well.
And finally, another crucial construction material, Greg Williams of Sublime Systems discusses how his team is decarbonizing cement. He contrasts their approach of avoiding emissions with the cost and complexity of carbon capture, laying out a pragmatic vision to achieve cost parity with traditional cement and dramatically reduce the embodied carbon of new infrastructure.
From a climate standpoint, how should we be looking at what you're doing, where you're kind of avoiding the emissions in the first place versus just capturing the emissions from cement production and then storing that? Like, why would this be better, or why is one better than the other?
Another good question. So, first of all, carbon capture is, I would say, still to be proven to be economical and effective at scale. There are a lot of pilot projects that are being built out right now. It's an exciting technology. Like we need all of these solutions in the industry. No one is going to get to scale fast enough to solve the problem. So, we root on these projects just like we do our own internal teams. But there is a lot of cost and complexity that comes with carbon capture. It can double the cost on a per ton basis of producing cement, can consume a lot more water, which is another precious resource. There is logistical complexity that comes with, like, once you capture the carbon, you have to do something with it. And so most cement plants are not built on top of rock formations that are suitable for storage of CO2 for 1,000 years. And then there isn't a ubiquitous network of CO2 pipelines built out to transport this material to where it can be sequestered. So there's the whole logistical complexity and cost downstream once you've actually captured the carbon. And for the majority of these projects, it's not capturing 100% of the CO2. There's still some emissions, so it's not fully effective. So again, like, tremendously helpful, can be a great tool, but our philosophy generally is if you can avoid even emitting the CO2 in the first place, eventually that is going to be a much cheaper, simpler, and more scalable solution. And you'll get kind of closer to that 100% reduction magic number.
Mm-hmm. Okay. So at the end of the day, yeah, just that's fundamentally a new process and cost that's going to be built into the cost of green cement based on carbon capture. And you project that Sublime Cement can get to sort of cost parity with Portland cement?
Yep, we do eventually. It's going to take some time. Like any new technology, we have to come down that cost curve as we scale. As mentioned, Portland Cement has had 200 years to cost optimize their process. And your typical Portland Cement plant is producing at least 1 million tons per year of cement. And we are operating at, less than 0.1% of that production scale right now. But yes, we have plans to build plants that are at similar scale. We have been fortunate enough to form partnerships with a couple of the actual cement majors that will help us to do so. And once we do achieve a similar level of scale, our models show that we have a path to cost parity with that cement production. The first full-scale plants, our target is having cost parity with the cost of OPC production if you include the cost of carbon capture, and then beyond, at some point, getting to pure parity with just cement production, even when you don't take the carbon capture into account.
So I hope those clips help to show some ways in which climate tech innovations will support all the AI data center growth in our future. Thanks for listening into this 2025 wrap-up episode. As always, I'm super grateful to every guest who shared their time with us this year, and to all of you who keep showing up, learning, and motivating us. I'm really excited to bring you more excellent conversations in 2026. Thank you for listening.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.